Welcome. We hope that this will be the first of a series of educational programs dealing with lightning and related issues. My name is Avram Saunders. I'm the president. See how important I am? I forgot my own badge. I'm the president of LEC, Lightning Eliminators and Consultants. We're out of Colorado, but we are here a lot doing business in the oil and gas industry here in Texas. We hope that this will be an interactive program. We want you to ask questions. We want you to engage with our speakers. They are Professor Al Gashevsky from the University of Colorado, who runs the National Oceanographic and Atmospheric Administration Environmental Technology Center. Did I get it right? Okay. And Peter Carpenter, who's chairman of our board, and he's going to talk about practical applications of technology to lightning. Al's going to do more on what is lightning and the issues that we're facing. I will say, from my perspective, that weather is changing in the world. The patterns are changing. I'm not even talking about global warming. I'm simply saying that the weather patterns themselves are changing. It used to be that Japan had the most intense lightning in the world. Well, we're now hearing that there's an area in the northern Atlantic off the Scandinavian coast that is as intense, and it's moving south. Used to be around the equator was the basic lightning belt in the world. That's changing as well. So we're seeing it in lots of places where we haven't seen it. The intensity has grown, the frequency has grown, and it's an issue that a lot of companies have not thought about directly, and we're encouraging them to give it consideration. And it's especially true in our observation that a lot of companies have squeezed out a lot of excess in their systems, whether it be manufacturing or whatever. They can't afford downtime anymore. And so lightning is one of those issues that can cause downtime very quickly and very dramatically. In fact, I think we have a slide on this in one of the presentations, but there were 3 fires related to lightning in the last week in Texas and Louisiana. So welcome. Please feel free to ask questions, interrupt, whatever. And with that, I'll turn it over to Dr. Al, as we affectionately call him.
Thank you, Robert. Give me about a half a minute to get the slides going over here.
For those of you in ties, feel free to be casual. Oh, in your bags, by the way, are the presentations, so if you want to follow along, they're in those bags. Make notes, whatever.
Okay, so thank you very much, Avram. I really appreciate you setting this up, Peter. And what I'd like to do is talk to you about lightning from a scientific perspective. So I'm not going to be talking about damage it does, mitigation of it, a whole other topic entirely, but rather what it's caused by and how in particular it's changing as a result of the changes that are going on in the global environment. So first thing I want to do is credit my good colleague Earl Williams, who is a faculty member at MIT and who really put this talk together. This is a talk he gave at the American Geophysical Union meeting in San Francisco last December. It was a very well-attended talk. It was actually the Franklin Lecture. This was after Ben Franklin. So Earl definitely knows his lightning, and I worked with him on a number of different studies, and so he suggested that I present this because it's a little bit easier for me to get here and all. Basically what I'm going to go over is a number of different topics. We're going to talk about the global perspective on thunderstorms, a little bit about something called CAPE, natural variations in temperature and lightning, and then how cities affect lightning, a little bit about how lightning is increasing in the high northern latitudes, which is coincidentally very much associated with what Avram just mentioned. Some things we don't know about lightning, how the sun affects it, and the things about where lightning occurs in the tropics, how that might be changing, a little bit about chemistry, and then some expectations. And basically, lightning is produced by convection. When we have convection, that is when we have water vapor condensing and releasing heat, that heat drives the condensed water up higher into the atmosphere because that heat, of course, represents a buoyancy. And as those particles now that are condensed out are driven upwards, some of them freeze, they turn into ice particles, snow particles. Some of them remain liquid, and that allows for a very efficient means of the charges to be separated. Literally, when you have these particles hit each other, there is a positive charge and a negative charge that are separated, literally electrons hanging on to one of the particles. And you have this huge charge separation where we can have really hundreds of coulombs of charge separated by distances of kilometers. And that represents what we call a dipole. And there's a very strong electric field in between. Eventually, that electric field gets strong enough to break the air down, and usually it happens just underneath over here. And when that air breaks down, we have a plasma channel that's created. That plasma channel propagates its way down to the surface, and then when it connects, that's of course when it does damage to things. But the reason that we have lightning is primarily thermodynamic. And so the strong view of how weather and climate affect lightning are through what's known as just the thermodynamic processes of convective available potential energy, which I'll talk about. And also what affects it, however, are aerosols. The very fine particles that are roughly micron size or smaller in the atmosphere, those affect this convection as well. And there's a minority view as well, and that is the more lightning we have, the more it affects things like forest fire initiation, which also produces aerosols. The more it affects atmospheric chemistry, which changes climate a little bit. The more it affects the clouds themselves. But this is kind of a small feedback. The majority viewpoint here is that weather and climate produce lightning through thermodynamics and aerosols. What really is important, however, is this convective available potential energy, or CAPE, as what it's known. And it's the dominant thermodynamic driver of convection, which is, of course, the driver of lightning. So we're going to talk about that. We're also going to talk about aerosols and how they influence convection as well. These are both crucial. And it turns out that as our climate is changing, and there's good evidence to suggest that it is indeed changing, the temperature changes are producing more CAPE, and the industrialization that goes on around the world is producing more aerosols. And so these are actually driving lightning changes to some extent. So you can ask, where does lightning occur? Lightning effectively occurs where there is convection, that is, where there is precipitation. So if you look at annual lightning activity, you'll find that it's concentrated over South America to a great extent, over Africa, and out over Asia. This is the so-called maritime continent. Over North America, certainly. But it's these regions where it's most prominent, these three in particular. And you'll also note that it's prominent mostly over the continents, not over water, with the exception of areas around Indonesia here. Precipitation, on the other hand, that's prevalent not only over the continents that I just described, but also over the equatorial regions. But over the oceans, the precipitation is not that intense. You don't have the strong convection that you do over land. So it's that convection that really relates to lightning, not just the precipitation. Now what's going to be happening is, as temperature warms, so does the ability of the atmosphere to hold water vapor. And so what we have is a so-called Clausius-Clapeyron relationship, which says that as the atmosphere warms, for every degree centigrade it warms, we're going to have the ability to hold about 7% more water. And that water represents the energy that's needed to cause convection. So as temperature increases, so does this convection capability, this CAPE. What is CAPE? Well, if you look at the temperature of the atmosphere, we know, of course, the higher up in altitude you go, the colder the temperature becomes. And you can see that with this line over here. If, on the other hand, you took a parcel of air and put it in a little bag, let's say, and then just lifted it up and up and up, just because the pressure decreases, that parcel of air would also decrease in temperature. but it doesn't necessarily change temperature at the same rate that the actual atmosphere does. The reason this is because the sun typically heats the surface, and we have more heating going on down here, and therefore this, what we call lapse rate, is larger than what actually occurs along this so-called adiabat. And it's this difference in between here, this area, that represents the convective available potential energy. So as you increase this altitude of this little bag of air and it cools down, it doesn't cool down as quickly as the actual atmosphere does. Therefore, it wants to keep rising. Therefore, it keeps causing convection. It keeps causing the air to further rise. So that's very significant when you have a lot of heat and particular moisture at the surface. And so you can ask, where is this cape largest? Where do we have most convection occurring? And you see it's predominantly in the tropics, but it's also very much concentrated over the three what we call continental chimneys. This is where a lot of the heat from the Earth, a lot of the heat from the surface, that is, works its way up in the atmosphere. So over Amazonia, over Central Africa, and a lot of it over Indonesia. So that's where we have most convection occurring. And a lot of different models say that. So you can look at different types of models. This is another one. This just happens to be the NASA GIST model. And again, what you see is most of this cape, this convective potential, occurs in these three zones. Again, a little bit over North America, but primarily these three zones. Now, what's the relationship to lightning? Where there's convection, there's lightning, basically. And we see that very clearly when we look over here on these charts where we have total lightning flashes. And over here we have the cape anomaly, which is the change in the cape from a normal condition. What we see is where there's more cape, there's more lightning flashes. Very clear. The cape is related to convection, and that's related to lightning flash rate. That's also related to the rain anomaly as well. This is rain intensity, precipitation. But again, I want to point out that this is typically over land where we have rain and lightning correlate. Over water, over ocean, we don't have that strong convection. We still have rain, but we don't have that strong convection that really causes lightning. So definitely the two are related. But we've also got now a role that's played by aerosols. And aerosols have been understood better and better over the years. The first aerosol map was produced way back in the 30s. And what this map shows is that a lot of the aerosols are produced by the land masses. There are indeed aerosols that are produced out over the open ocean, usually sea salts. But most of the aerosols that are associated with dust, even in pre-industrialized times, 1934 is somewhat pre-industrialized, these aerosols are produced by essentially mineral dust. If you look at what's going on today, that aerosol distribution map has changed pretty significantly. So since 1934, what's happening is in industrialized areas, in particular areas where we don't have too much concern about the emission of aerosols, or we have a lot of fires, people cooking over open fires again, somewhat primitive conditions, that's where aerosol loading in the atmosphere is very large. Some of this is also the result of desertism as well, desertification going on here. But you can ask, what do these aerosols do? And the answer is, when you have aerosols, those particles themselves attract moisture. They take the water vapor in the atmosphere and they turn it into small drops. And they don't allow the drops to grow very big and rain out. Instead, those small drops end up collecting water, not getting the big drops, but instead become lofted up by the heat that's released by the collecting of the water. And they increase the vigorousness of the convection. So what they do is basically encourage the water vapor that's around to form droplets. When that water vapor forms a droplet, it releases heat. That heat drives convection. And basically the aerosols themselves become seeds of convection. And so when you look at various parts of the world that are producing a lot of aerosols, urban areas in particular, that we'll see as we go along, we do find that there's more convection going on, stronger convection. Figuring out how this fits in and coming up with a good model is actually pretty hard, though. There's no doubt that aerosols play a role. There's no doubt that temperature plays a role. And you can come up with ways of quantifying it. I'm not going to go into that in too much detail. But it just turns out that both of these effects work together to produce more convection and, at least locally, more lightning. So let's take a look at natural variations now in global temperature and lightning. How temperature varies around the globe, how lightning varies in response to it. And you can look at various time scales. You can look at the daily time scale or diurnal. You can look at the semi-annual time scale, the annual, and then you can also look at episodic variations like El Nino that cause variations in convection and therefore variations in lightning. And when we start looking at lightning, we can ask, what sort of indicators do we have of it? Well, we've got, of course, reports of lightning strikes. But we've also got other ways of looking at just how much lightning is occurring. And a couple of them are illustrated right here. The more lightning we have, the more convection that is that goes on, and the more lightning that goes on, the more charge that we have pumped up into the ionosphere of the Earth. And as that charge gets pumped up in here, what actually happens is it's kind of like a capacitor. We've got a big plate around the Earth in the ionosphere. We've got the surface of the Earth. And the voltage, literally the voltage between the surface of the Earth and the ionosphere increases. And you can actually measure that voltage increase by measuring the electric field strength at the surface. So as we build up charge in the atmosphere, in particular as we get more and more lightning going on, that voltage increases, the electric field strength increases, and we can measure that. There's another way we can measure it as well, though. And that's through something called the Schumann resonance. This capacitor system of this plate and that plate, it actually forms a resonator. It forms a cavity. And just like inside a room where you have acoustic waves resonant, the more noise activity that goes on, the more noise overall builds up in the room. It doesn't dissipate. And that's what happens in this wonderful capacitor. The more thunderstorms we have, the more electrical noise there is that's caught in this resonant shell as well. And so we can measure that, and we can look at essentially the power spectrum of that noise. All those resonances are somewhere about 7.9 hertz, actually. It takes about that much time for radio waves to propagate around the Earth. And so as we listen for this noise and look at the frequency of it, listen for the frequency of it, we can tell pretty much how much lightning activity is going on the globe. How else we can do it? Something called thunderstorm day, which is rather crude, but it's still effective. And a thunderstorm day is an observational day at a weather station where thunder is heard. Pretty low tech, but it's also pretty easy. This is actually still a pretty reliable metric for lightning occurrence. I do want to point out, though, that it measures thunder, it doesn't necessarily measure lightning. How else can we do it? Well, we can look down on the Earth and look for flashes from satellites. So we have satellites in geostationary orbit that look for flashes. We have satellites in the low Earth orbit that look for flashes. And they count these flashes. And it turns out that the lightning flash density pretty much matches where we have high CAPE over land areas. And again, not over the water areas because we don't have as much convection going on over there. But over the land areas, in particular South America, Africa, Indonesia, that's where we see a lot of flashes. Now, these flashes, generally speaking, happen according to this curve, this so-called Carnegie curve, where the flash rate is highest in late afternoon. Why is that? Somewhat simple. It takes a little bit of time for the Earth to heat up during the day, so as the Earth is rotating and the sun is beginning to shine at a particular location. That location takes some time to heat up, and it's in the late afternoon when that convective available potential energy reaches its peak. That's where we have the convection then. That's where we have the highest flash rates. So if you look all around the globe, generally speaking, you have curves of this nature. Most places in the world as well will exhibit this peak later in the afternoon. There are 2 places where it's actually earliest, and those are anomalous. But again, most of them in late afternoon. What happens when the temperature increases? Well, it's been shown that the voltage in the ionosphere also increases. It's usually at somewhere around 260,000 volts or so. A lot of people have thought, well, gee, that'd be a great source of energy. Why don't we put a wire up there and tap it? No, don't run to the patent office. You drain the ionosphere in about a week of lighting the lights in a given American home. There's really not a lot of energy in it, but there's a lot of voltage in it. Nonetheless, it turns out that as the average temperature in various land masses increases, so does that potential. And again, that indicates that as temperature increases, the lightning flash rate increases, more charges pumped up into the ionosphere, therefore the field strength increases. And we can measure that. Note here too, this is actually a pretty important figure. This change is about 7% per degree centigrade. And that's about the same change in the amount of water vapor the atmosphere could hold per centigrade. We go way back to that Clausius-Clapeyron relationship. What that tells you is every centigrade of warming basically produces about a 7% increase, roughly speaking, in the flash rate of lightning.
So Al, may I?
Go, please, yes.
So if I understand what you just said, assuming that the science is correct, that the word Earth is warming, does that indicate, based on that calculation, that we're going to see more and more lightning over time?
That is the implication. And in fact, you're jumping to the conclusion, but with some caveats.
Okay.
Because not all the evidence points directly to that.
Okay.
There's just some null evidence yet. It has to be brought out.
Okay.
But that seems to be the conclusion. So, you can look further. You can ask, what about what happens during the year? And the Earth itself has a tilt of 23 degrees out of the so-called ecliptic plane. That's why we have winter and summer, basically, because as the Earth rotates around the sun, its axis is always in the same direction, and during winter, the northern hemisphere gets less sunlight. During summer, our summer, that is, the northern hemisphere gets more sunlight. But as the Earth rotates around the sun, in the spring and in the fall, that's when the sunlight is primarily falling on the equator, on those land masses that have particularly large propensities for CAPE, in other words, where a lot of the lightning occurs. And what we see is the mean insolation that is absorbed by the Earth tends to go through a couple of peaks in both the spring and the fall. The temperature also, as a result of that, the global average temperature goes through a couple of peaks. But the globe is not the same temperature if you average over all area of it throughout the year. It does change. And as a result of that, the lightning flash rate as well, in particular in those regions that are fairly close to the tropics, that also undergoes a couple of cycles. So again, this is evidence, pretty strong evidence, of a warmer atmosphere giving rise to more convection, giving rise to more lightning. And at about the same, roughly 7% per degree. And this is also echoed in a lot of other signatures. You can look at, for example, the Congo River discharge, the flow rate, in other words, out of this river, this basin. And what you see is, again, this double hump curve. We have a peak here, another peak over there. Again, more convection is occurring, more rain is occurring, and so we get these two peaks. You can also look at what happens over the entire globe. When you average over the entire globe, you don't see these peaks, these two peaks anymore, you just see one big peak. But this one big peak also corresponds to a global increase in flash rate. And if you look at that flash rate, that's pretty significant. It peaks, by the way, in June, July, and August. So averaging over the entire globe, northern southern hemisphere, we tend to get more lightning in June, July, and August than we do any other time of the year. Again, look at the change here, about 11% per degree C. So again, it kind of falls in line with 1 degree C change, generally speaking, increases convection and flash rate by around, again, give or take 7%, in this case 11%, but roughly that number. And you can look at it from the standpoint of the satellite imagery as well, the flash rate, and what you find out is in June, July, and August, if you just average over these pictures, it's kind of hard to do with your eyeball, but if you averaged over them using a computer, you'd find out indeed that the maximum is in June, July, and August, and these are the locations of the maximum. Again, Africa, very significant. In this case, the southeastern U.S. actually, area around the Gulf Coast, very significant. And what's also significant is the maritime continent in Indonesia. So again, a lot of these things just point to, again, warmer atmospheres, more convection, more flashes. Then you can start asking, what happens when you have these episodic events like El Nino? We know the El Ninos come and go, and we don't quite know exactly when they're going to be coming, but when they get set in, they usually stay for about 9 months or maybe a couple of years. El Ninos do modify the ability for hurricanes to form. So when we in particular have an El Nino phase, generally speaking, the winds are blowing in a way that keeps hurricanes from forming in the Atlantic. And in the opposite case, there's more likely a hurricane to form in the Atlantic. So they actually have a pretty significant effect on it. But they're also very random effects. But you can nonetheless ask, do they affect lightning? And I'm just going to skip these references and then just go right to the chart. The answer is that during an El Nino phase, in some parts of the world, Asia in particular, the maritime continent region, the lightning flash rate can almost double. So when you go in and out of this El Nino phase, because of the change in the amount of convection going on in various parts of the world, it does shift where convection occurs, in other words. You do indeed get changes in flash rate, I should say, again, a roughly factor of 2 or so, depending upon the location. So it has a big impact. What about urban areas? Well, what does an urban area do that might increase the amount of convection going on? 2 things. One is the built infrastructure creates a heat island effect. We all know that very well. That's why we try to get out of the city on the weekends. And that heat island effect increases the temperature in the lower atmosphere, which increases the amount of convective available potential energy, increases the K. The second thing that urban areas do is increase the amount of aerosols in the atmosphere. Cars, trucks, buses, anything that kicks up dust that's on the streets, for example. That all contributes to aerosols. That all contributes then to a more easily disturbed atmosphere, which then has more convection. And so you can see that over here. If you look over at Houston itself, we find that lightning over the Houston area is greater than in the surrounding areas. It's very typical of many urban areas, so don't feel singled out here. No, it's not. And it also is growing with time as well. So if you look at, for example, Sao Paulo, what you find is the number of thunderstorm days, in this case over 50 years, is growing. This is apparently not because of people hearing more thunderstorms either, so this data has been normal. And it's also consistent with the temperature, the average temperature in Sao Paulo, which is also growing. This is growing at a particularly large rate, but this is because it's an urban heat island. But again, what you see is around a 10% change in the number of thunderstorm days per degree C. Further evidence, this I find rather interesting, is that the flash rate is pretty high during the week, and on the weekends it drops by a pretty significant amount. Why is that? It's because you have less aerosol production on the weekend. There's a little bit less driving that goes on in cities. And we see that very clearly. This has actually been shown with precipitation as well. There have been studies using satellites where you measure precipitation. Turns out that it takes a break on the weekends. In urban areas, I want to point out too. Now, these aerosols play a significant role. But I don't want to make the picture too simple because it actually is a little more complicated. When you really start loading the atmosphere with a lot of aerosols, it gets to a point where you've got so much aerosol in the atmosphere, it causes the moisture to rain out quicker than it would otherwise, and it actually can then work against you. So it turns out as you start to increase the aerosols, the flash rate increases, the convection increases, but then when you get to a point where you've got so much aerosol loading in the atmosphere that it rains out the atmosphere quickly, it actually causes a reduction in convection. So these are some complicated effects. Aerosols come in first off to support convection. When you get enough of them present, they actually reduce the amount of convection and the amount of lightning as well. What about in the northern latitudes, as Avram mentioned? Well, these are the global temperature trends. This is from the NASA GISS model. And this is throughout the last century, essentially, 1900 to the present day. And if you look at the various different regions, the tropics, southern latitudes, and the northern latitudes, what you see is that in the northern latitudes, this is where the temperature increase is most pronounced. We get about roughly half, roughly about 2/3 of those temperature increases that we're seeing in the northern latitudes in these other regions. And so it stands to reason then that we're going to have more convective available potential energy and therefore more lightning in northern latitudes. And indeed, you go to places like Fairbanks, Alaska, 65 degrees north. Alaska is, of course, undergoing very significant temperature increase. What we see is that the thunderstorm day count has been changing rather significantly. This is from 1950 to 2010, about 300% change per century. So people in Fairbanks, for example, who rarely heard thunder are starting to hear it a lot more. And this is the temperature trend as well. If you look at the temperature trend, it tends to line up very close. Again, what we see is around, in this case, 3.2 C per century of change. That's a lot compared to the average. The average around the globe is about 1 degree per century at this point in time. But over in this region, in the northern latitudes, because we have this enhancement, we see a lot more of a change and therefore a lot more increase in lightning. So one of the upshots of this is that in regions like Alaska, which can probably extend, for example, to the north coast of Alaska, as global temperature increases, we could expect to see about 3 times as much of a change in convection and therefore 3 times as much of a change in lightning. Do we know everything about this phenomenon? No. There are a lot of interesting issues having to do with why the sun tends to change the amount of lightning that goes on as well. The sun goes through solar cycles, which occur on around an 11-year basis. And during these 11-year cycles, there's a great deal more sunspot activity. There's a great deal more activity that produces flares, solar flares. And this activity also causes the sun to eject more particles, charged particles which then stream towards the Earth. Those charged particles interact with our Earth's own magnetic field, and they twist and otherwise distort the lines of the Earth's magnetic field. Now this happens at high altitudes, way above the atmosphere where most of our weather occurs. But it does have an impact on lightning, and this is seen by looking at the thunderstorm day, what we call power spectra, where if you look at the thunderstorm day power spectra, you often find in many places around the globe an 11-year frequency peak. In other words, things are happening on this 11-year cycle, which is without question connected with the sun's solar cycle. Why that's occurring is another question, and we don't know the answer yet. We see that not only in thunderstorm days, we see that in the energy content of the Schumann resonances. during what's known as solar max. The last one of them was 2002. The next one is going to be next year. Basically, what we see is a lot more energy occurring in solar max, which means a lot more lightning activity occurring in the peak of the sun's 11-year cycle. And again, why this is occurring is not necessarily well understood.
You're saying next year will be the peak, that's right?
Next year is going to be the peak, right?
Will it go down a little bit, start back up again, or?
Well, it'll go down, and then there's an 11-year cycle. Yeah, so basically, it's going to be 2014 peak, the next peak will be in 2025.
Based on the sun?
Based on the sun, right. Now, we can also take a look at long period trends and stability of these tropical chimneys in places where there's a lot of convection going on, these three locations, South America, Africa, and Indonesia. And you can first start asking, well, how do we measure lightning strikes? And I mentioned a couple of ways. We also now have lightning detection networks that operate by radio means. They basically listen for abrupt changes in the noise in the radio spectrum, and by triangulating, they determine where lightning has struck. And these have an accuracy of, give or take, roughly about 10 kilometers or so. So they can pretty much tell where lightning is striking over the U.S. There's a very active area of research right now in trying to make these better, more precise, so that we can know, in particular out in the West where we're very prone to fires, where lightning has struck within about 100 meters. If we could determine on a real-time basis where that has struck within 100 meters, we'd be able to send out crews before these fires became unmanageable. And it's a big issue out in the West, especially as we enter a drying phase. And when you look at the data, you find out here that indeed the number of strokes has gone up tremendously. The issue here, though, is that there are more of these networks around the globe, and they are more accurate as well. They're more precise and more sensitive. And so this is not really a good indicator of the number of strikes that have been going on over the past 50 years. We have to look instead at other indicators. This is the case of what we call a biased observing system. It's a great observing system from a lot of standpoints, but it's also a biased observing system. So ground flashes, even though they've been going up tremendously, a lot of this is a result of just better coverage with the networks. We can look at other measurements, though. The electric field near the surface of the Earth. This is data from the Kennedy Space Center. This is the Z component, or the vertical component of the electric field, which is normally around 100 volts per meter. And that has been slowly going up. Again, this sort of echoes this roughly 7% per degree change that's been going on. You can also see a slight trend if you extrapolate this over the globe. But I do want to point out that this is not what I call statistically significant. It's a kind of an interesting trend when you draw the line through, but the statistics are not precise enough really to take it to the bank, so to speak. Nonetheless, it's about at the same rate, which is interesting. You can look at other things too. You can look at the record of the current that flows through the air. When you have this ionosphere above us that's charged up to almost 300 kilovolts, there's a steady flow of current. It's a small current, but it leaks its way through the atmosphere, and it causes that ionosphere to discharge. If it weren't for lightning, the ionosphere would discharge within a couple of weeks. That current itself, when you measure it very carefully, it's exhibiting a trend. And again, it's fairly consistent with the kind of roughly 7 to 10% per degree C trend that we're seeing in lightning. You can also look at the river discharges occurring. River discharge is associated with rain, which is associated with convection. And when you look at, for example, the high water marks on, this is in Manaus, in the Amazon basin, what you see is a small increase, again, commensurate roughly with the scale of what we've been speaking about. This is for the Congo River as well. Again, slow increase in river discharge.
When you say discharge now, you mean actual water flow out of the river into the
Water flow out of the river, exactly, yep. Yeah, these are very lightning intense regions as well. You can also look at it from the opposite standpoint. And when you look at global temperature trends throughout the last century roughly, you see some interesting trends. It's been increasing in the industrialized era. It tended to level off right after World War II. And this is largely attributed to the slowdown in economy around the world after World War II. There were a lot of countries that were rebuilding. Their economies were in shambles. The U.S. was one of the few countries that was in good stead in that regard. And then it wasn't until about roughly 1960 or so when many economies in the world started industrializing, and we see a global temperature trend that's more in line with what is currently happening, which is roughly currently about 1 degree C per century. But there was this lull period here as well, and you can ask, what happened during that time? And the answer is, there was a decline in thunderstorm days during that period of global and regional cooling. It was really more of a lull in the cooling. When you look at the thunderstorm days, that tended to level off in that time period. So, a lot of this data is fairly noisy, but it tends to correlate well with increased temperature and increased aerosol loading, causing more convection, causing higher flash rates. I'm not going to say that all the data suggests it, and this is a bit of an anomaly. This is data from the lightning imaging sensor, that same sensor that was used to determine where flashes are occurring around the planet. And when you look at the global flash count rate for the past roughly 12 years, you find out that there's really not a statistical trend in it. It's not increasing by that 7% per degree C that we would expect. Now, in the last 10 years, we don't have a degree C rise, we have more like about a tenth of a degree C rise. So you would expect roughly a 0.7% increase in the global flash rate. We don't see that. Why that's occurring, we don't quite know. So even though a lot of the data tend to be consistent and agree, there are some anomalies, and this is one of them. One of the hypotheses that one could look into, I'm not sure if anybody is doing this right now, I think it's an interesting thing to do, is the following. If the convection intensity is increasing, yet the amount of cloud that's lofted above the region that produces the electrical discharge is also increasing, that might be hiding some of the flashes, and it may be making them less likely to be seen by the sensor. That's, at this point, a complete hypothesis.
Something from satellite sensors?
A satellite sensor looking down, correct. Literally, it's counting flashes.
In those flashes, unfortunately, I have some curiosity, as far as your data goes. Would those be also like recording cloud to cloud, intercloud and cloud to earth?
They would.
So they would, it's not to define what it was, it's just a flash.
It's just a flash, exactly. Yeah, they don't differentiate between cloud to ground or cloud to cloud. But if there is more cloud above the regions as a result of enhanced convection, it may also reduce the ability for those flashes to be sensed. So, again, that's a bit of an anomaly. What about atmospheric chemistry? Well, there are certain things that lightning does that's actually beneficial for us. One of them is it produces ozone. And the ozone it produces is up at high altitudes, and because of the convection, that ozone is lofted up into the stratosphere exactly where we want it. So, in spite of the fact that we've been destroying ozone by producing various chemicals, refrigerants in particular, a lot of them have been phased out, but some countries still produce the damaging ones. We also have a mechanism here which is, to some extent, counteracting that and producing more ozone, which is good. So what happens is, as we all know, in an electrical discharge, if you ever sniff the air around a motor, for example, where there's a lot of sparks because of the brushes, you smell the ozone. That's exactly what happens as well. In a thunderstorm top, that ozone gets lofted up into the stratosphere. It's a good thing. What do we expect coming up then? Well, it's pretty clear that the Cape is going to be increasing with temperature, but it also depends on where in the atmosphere the temperature rises occur. If the temperature rise occurs at the surface versus higher up in the atmosphere, that's going to change the Cape a little bit more. In fact, The strongest Cape change will occur when the temperature rise is at the surface, because that's what tilts the lapse rate of temperature in the atmosphere most. So when you start looking at what's going to be happening in the future, you really got to ask, is the lower atmosphere going to be warming, or is the atmosphere as a whole going to be warming? And there are people studying this right now with global climate models, or GCMs as they're known. These are a couple of different ones. And what they're suggesting is that there'll be larger amounts of cake, but less often. And this is a rather interesting issue, because even though you think, well, the larger amount of cake is going to produce more convection and more lightning, it does turn out that the lightning is most prevalent when the cape is large but not too large. So somewhere in this vicinity is actually where most lightning will occur. And so as we start looking at the predictions, it's not necessarily clear, at least from this standpoint, that we would get a lot more lightning. So far, when we start looking locally, all the indications point to it. The GCMs don't necessarily point to it. And the same thing goes with the modeling that people have been doing with regard to El Nino and La Nina. They tend to indicate slight differences in the flash rate distribution, but it's not really what you'd call conclusive. In some sense, you can say that the models at this point really aren't matching those observations that tend to mostly agree regarding increased flash rate associated with temperature. And so, what about lightning in our future? From the thermodynamic viewpoint, more lightning is probable. A lot of these mechanisms, again, seem to be being observed in different ways. They tend to agree with each other, roughly quantitatively. And this would be especially the case in the northern latitudes due to increasing Cape. With regard to aerosols, this is a little more difficult because, again, this nonlinear relationship between aerosols and convection. Enough aerosols can actually start reducing convection. But it currently appears, definitely in their urban areas and industrialized regions, that this is producing more convection and therefore more lightning. The observations that we have, most of them, but I won't say all of them, indicate more occurrences of flashes, higher flash rates. So, let me summarize, and I'll be happy to take some questions then. Both the thermodynamics and aerosols are influencing lightning activity, we believe. Disentangling these two effects is a challenging task, but it's very clear that Cape is part of the issue. Lightning activity in cities and at high northern latitudes is on the rise. Long-term trends in tropical chimney regions are slightly positive. There's an unknown effect caused by the 11-year solar cycle on thunder days. There's a possibility this might have something to do with galactic cosmic rays, which decrease during the 11-year solar max. But that's, again, speculation at this point. There's no fundamental mechanism that we really see to connect the two. Generally, we expect more lightning in a warmer world. And the temperature trends that we see now suggest that that is indeed the case. Lots of ways we can observe lightning as well, using the global electrical circuit, for example, using satellites. This under-detection anomaly in satellites also deserves some attention. And with that, since this was part of the original Franklin lecture, Earl wanted to acknowledge Ben Franklin, who was, of course, our original lightning scientist, and still invented a device that we use very commonly. Of course, that LEC is producing now a different device that works on a different principle. Lightning is a very complicated topic, I want to point out, though. And in just looking at these various trends from sensors, from observations, etc., we can just start to get what we call a good feeling for what's going to be happening in the future. But I do want to point out that there's still a lot of things we don't know about it. The microphysics of it, for example, is just one element. How the sunlight, solar maximum, for example, not the sunlight, I should say, but the solar max, how it affects it. Those are other things we don't know about it. And so there are a lot of things that are still going on that are relevant in the area of research. And I'm just going to end at this point Be happy to take any questions on this that I can answer. So please.
Now, the conclusions seem to be that we're moving towards more lightning. What about intensity of the lightning? Is that changing as well?
Really, I don't have any data on that. And I honestly don't think we have any data on that because flash rate is the fundamental parameter that we measure. We measure number of flashes, we measure the locations. Thunder days, for example, are really determined based upon whether thunder occurs. It's not a measure of whether it's loud or not. And so that's not something that I don't think we can really comment on right now. Okay. The other thing that happens is when you have a plasma channel open up from a cloudy ground or intercloud, generally speaking, those channels open up and yeah, we do see strikes that are of various different intensity. But when they open up, it's usually a result of the amount of charge up top. And that's related to the convection potential. But to suggest that we're getting stronger strikes, you know, I just don't think there's any data available on that right now. I'm scratching my head trying to think whether we have any available. I just don't think we do. Question?
I'm aware of an observation up on a mountain, I guess it's in Maine, probably the most struck place in the world.
Mount Washington, perhaps?
Sorry?
Mount Washington, perhaps?
Perhaps. But there is an observation, lightning observation station there.
Yeah.
I'm just curious if they hadn't put some instrumentation to gauge the amount of power that's being released in those strikes.
Yeah, that's interesting. You know, if you go up to the top of Stone Mountain in Georgia near Atlanta, you'll see a number of pits in the rocks. And in fact, anytime you're hiking, you see a mountain where there's a bald, you'll see these pits. I don't know of any instrumentation on the top of Mount Washington. I'm assuming you're referring to that because Mount Washington is very heavily instrumented. In fact, there's a base, an outpost up there on the top of Mount Washington. You regularly stay up over there. But as far as the intensity of the currents in the down conductors, to my knowledge, there are no recording instruments.
Well, maybe that it's such a large release at one time that we just, we don't have any instrumentation that can respond to it.
I don't think that's true. I think that can be built. You know, it's a current that ranges, generally speaking, between 10,000 and 30,000 amperes and exists for a period of basically around a millisecond or a little bit less than that. I don't think it's unreasonable to consider measuring, but you really have to look very carefully at how to do it because the potentials along the wire itself can produce electric fields transverse to the wire that can affect the instrumentation to a great extent. And I think the answer, really, the short answer is that people just haven't really tried to measure it, and in particular look for trends. We know that these numbers are appropriate, 10,000 to 30,000 or so roughly. But as far as trends, that's another story.
Well, that would require measuring it over time. So if we haven't been measuring it, then of course.
Yeah. Yeah, the measurements basically have been made to show us the amounts of current, but certainly not trends.
And there was some talk years back about trying to capture that energy. I don't know if there's anything that can respond rapidly enough to absorb and contain the power that it
And that is the problem, right? It's got to respond very rapidly, not within a millisecond because that's the entire likely stroke, but more likely within about a tenth of a microsecond or so. And so to be able to channel charge into some capacitor or some device that's going to either build a magnetic field and use that and slowly dissipate that, I don't see that happening. A big Leyden jar.
Leyden jar, yes.
You mentioned Fairbanks as an example of increased lighting frequency. I was wondering if you have data in any other northern applications that normalize for heat island effect. And
Yeah, and you could ask whether Fairbanks really is a heat island. If you've ever been to Fairbanks, it's really not much of a heat island. You know, there's a lot of dirt roads around town. So I honestly would not think that Fairbanks had a significant heat island effect. The other thing I will point out, though, and by the way, I don't have any data offhand at other places that are not affected by potential heat island. But there was just a fairly concerted study of the heat island effect on global temperature measurement. And the hypothesis was that these temperature readings are being taken in cities where there's a heat island effect, and therefore the temperature curves that we're seeing as a function of time are somehow biased. And so what this study did is looked at the nighttime lights in the U.S. And there are places where these nighttime lights are bright and not. You know, Houston, Denver, all on the East Coast, you see very bright nighttime lights. Those are the places where people live. Those are the places where we have built infrastructure. Those are the places where we have heat island effects. And so what they did is they took all the temperature measurements that are taken at these surface stations that are in the heat island regions and outside of them, where there's little nighttime light. And basically the answer was that there's almost an imperceptible difference. So the urban heat island effect is not affecting those temperature readings that are being taken, in other words. Insofar, I want to point this out, insofar as the global trends go. So when you look at the global trends, subtracting those locations where there's a supposed population density of significance, the trends just aren't any different. And so, you know, when I look at Fairbanks, for example, which is not much of a heat island, and then when I look at other data such as this, where you subtract those measurements that might be biased, and there's really no change in the global curves, I don't see a significant impact of the heat island effect in the global temperature data.
do you have any other, okay, so heat island aside, do you have any other northern data that shows similar trend or what we saw in Fairbanks?
I don't personally have that. It might have been taken, but I'm not aware of it at this point. Would be interesting to get one. Yeah.
Question regarding offshore oil facilities, platforms, even drilling rigs. Do you have any information about lightning strikes directly affecting them?
I think LEC would probably have more direct information on that, but a lot of it depends on how close it is to land. The Cape effect is strongest over land, where you have the surface heating the boundary layer, and it tends to taper off pretty quickly, roughly 10
Even
miles
in
or
the
so.
Gulf region, when those strong fronts come through?
Pardon?
I said even in the Gulf region, down here where the strong fronts come through and tend to build up large potentials?
It depends on the stability of the boundary layer and the amount of heat in the boundary layer. If you have a weather pattern that's producing a very warm boundary layer because you have flow off the land that's warming up that low layer, then that's going to tilt the lapse rate, and that's going to increase the Cape. So, in some sense, it depends on the flow. But if you didn't have flow, basically you get about a few scale heights of the atmosphere, in other words, perhaps 10, 20 kilometers offshore. And you've already got a meteorological condition where the boundary layer is dominated by the temperature of the water. So, as all know, water has a very high heat capacity. Its temperature doesn't change very much, certainly diurnally, changes seasonally, but not very much diurnally. That's going to be a stabilizing influence as far as Cape goes. But that's not going to guarantee that you don't have a warm air layer that's tilting the lapse rate that's a result of a meteorological flow.
Ordinarily, when we get these strong fronts through, we actually have cold air lifting or running under warm air, which gives you the long
Right,
lift
right.
factor and increases the cloud tops. I don't know.
Yeah, now,
Casual observer.
that's a situation that is not going to necessarily give rise to a higher Cape load.
Okay. I do know I've been offshore and seen storms There's also some pretty good lighting, even significantly offshore.
Yeah, it's not to say that it doesn't exist. It's really a matter of just how often it exists. And how often we have the situation where there are is stratification, where there are layers that produce the steep lapse rate. It's really a function of the lapse rate. The steeper that lapse rate is, in other words, the quicker the atmosphere gets cold with height, 7 degrees kilometers typical, per kilometer is typical, but it can also become steeper depending upon the layering. Then the more propensity there is for convection. More easily that a parcel lifted from down below is then going to produce heat as the moisture condenses, which produces more buoyancy, which then causes the whole situation to go unstable and produce convection. The aerosols confound the picture a little bit more.
So the drawings, the statistics, the numbers that you're showing, lightning strikes, flashes, whatever, is there any difference in cloud to cloud, cloud to ground? Do any of those numbers change depending upon whether the horizontal or vertical?
So the thunder days basically are cloud to ground. We generally speaking don't hear as much in a cloud. The flash rates are going to be observed both cloud to ground and cloud to cloud, and those are going to be pretty comparable to each other.
By that, you say that the lightning is about equally distributed cloud to cloud, cloud to ground?
Well, no, that's not the case, not necessarily, no.
Okay, that's what I'm...
Yeah. The way that the dipolar discharge occurs is that, generally speaking, we have negative charge or positive charge. That's the typical mode. It doesn't always occur that way. That negative charge down below will produce a very strong upwardly pointing electric field that usually will initiate the plasma channel at the base of the cloud. And then when that plasma channel opens and connects to the Earth, then we have the leader connecting to the streamer, very strong flow of current. And at that point, we also will typically have a backrush of charge from the Earth, which is going to be using that plasma channel. What happens above that then is that charge, the positive charge now, has to draw negative charge from the ionosphere to neutralize itself. And that happens through a variety of mechanisms consisting of what are known as elves and sprites that are discharge mechanisms that happen in a thinner region of the atmosphere. The atmosphere is a lot thinner up there, density that is. And so one has this transfer of charge going up to the ionosphere then through this other process, which is more cloud to cloud.